This video will help you to understand Dijkstra's shortest path algorithm. A shortest path algorithm is run on a weighted graph. It starts with an initial node and a goal node, and it finds the least cost path from the initial node to the goal node. Dijkstra's algorithm assigns a tentative distance value to every vertex or node. It makes it 0 for the initial node and infinity for the rest of the nodes. It also creates a visited set, which initially just has the starting node, and an unvisited set, which starts with the rest of the nodes. It starts running at the initial vertex. For a current vertex, you add the vertex to a visited set and remove it from the unvisited set. Then you calculate the distance to the current vertex plus the weight of the edge between the current vertex and its unvisited neighbors. If this value that you calculated for each of the neighbors is less than the current stored tentative distance to that vertex, you replace the stored distance with the newly calculated value. This algorithm may seem kind of complicated right now, so let's see how it works on a graph. Here's our weighted graph. A is our initial state and F is our goal state. A has been marked red and it's been added to our visited list. Also notice that we've added tentative distances to all of the nodes. It's 0 at A because that's our initial state, and it's infinity at all of the other nodes. So we start the algorithm running at A. A has 3 neighbors, B, C, and E. We need to calculate new values for B, C, and E by taking the distance from A to A, which is 0, and adding that to the edge weight between A and B, A and C, and A and E. So for B we get 4, for C we get 3, and for E we get 7. Since all these values are less than infinity, we update the distances at B, C, and E. Now we need to pick the next unvisited vertex with the lowest calculated distance. This is C with a value of 3. We add C to the visited set. Since C is a neighbor of 3 unvisited nodes, B, D, and E, we calculate new values for B, D, and E. The distance to C is 3, and we add it to the edge weights between C and B, C and D, and C and E. For B we get a value of 9. This is higher than its current value, so we ignore that. For D we get a value of 14, which is lower than infinity, so we replace D's tentative distance with 14. And for E, we get 11, which is more than 7, so we ignore that value as well. Now we visit the next lowest distance vertex, which is B with distance 4. From here, we only recalculate distance to D since C and A have already been visited. We calculate 9, which is lower than 14, so D's new distance is 9. Next we visit E because it has a weight 7, which is lower than D's weight of 9. From here, only G's calculated distance is lower than its currently calculated distance, so we update G's tentative distance with the value 12. At this point, we have 2 vertices that we could visit. D has the lower tentative distance, so we visit D. From here, we calculate new values for G and F, but the calculated distance is higher than G's current tentative distance, so we ignore it. For F, the current value is infinity, so we replace it with this new value, which is 11. Now the vertex with the lowest tentative distance is F. We visit F and add it to the visited set. Now we've reached the goal and we are done. The shortest path from A to F is A to B to D and then to F. This is a pseudocode description of Dijkstra's algorithm. It uses a min heap to keep track of which vertex has the lowest tentative distance. This is the complexity of Dijkstra's algorithm, assuming that you use the binary heap to keep track of which vertex has the lowest distance. E and V are the number of edges and vertices in the graph respectively. Note that this algorithm has a different time complexity from graph search algorithms. This is because the binary heap adds and removes elements in log v time, whereas the data structures that you would use for the graph search algorithms adds and removes elements in constant time. And that's it for Dijkstra's algorithm. I hope this has helped you to understand it better.